Hello, chemists. This is Ms. Placino, and you are watching lesson 4.3 on covalent bonding. Today's lesson is a really important one. This is going to kind of be at the center of everything else we talk about this unit. What we're going to focus on today is how to represent covalent compounds, so compounds that are sharing electrons using Lewis structures. Super important. So goals for today's lesson: define what a covalent bond is and predict when one will form. Represent covalent compounds using Lewis structures. This is the big one for today. And finally, determine which atoms in a molecule or ion will have formal charges and assign them. It's a little bit of an advanced topic, but I know you guys can handle it. All right, lots to do today. Let's get started. Covalent bonds. Covalent bonds are going to form between nonmetals only, and for our purposes, we're going to treat metalloids as nonmetals as well. So elements like boron and silicon, for example, they're more nonmetallic in nature, and when they bond with nonmetals, they're going to behave as nonmetals. In a covalent bond, we have the sharing of electrons. So if you look at this kind of picture that we've got of CH4, the red electrons are the ones that carbon is bringing, and the green electrons are the ones from hydrogen. And every place we end up with those two electrons paired up, we have a bond. The orbitals are going to overlap, the electrons will be shared, and carbon will complete its octet. It's got 8 electrons around it. Hydrogen completes its duet. Hydrogen maxes out at 2 electrons in that first energy level. If you have 2 electrons present in a bond, that is a single bond, also called a sigma bond. And we'll be talking more about sigma and pi bonds in a future lesson. Just jot it down for the time being. We will revisit it. If you have 4 electrons being shared between 2 atoms, yeah, that's a double bond. A double bond consists of 1 sigma and 1 pi bond. And in the event that you've got 6 electrons being shared between 2 atoms, that is a triple bond, and that has a sigma and 2 pi bonds present. There is no such thing as a quadruple bond. 2, 4, or 6 electrons can be shared only, giving you a single, a double, or a triple bond. All right, let's talk about drawing covalent Lewis structures. We'll walk through one together and we'll try some practice problems. Based on a Lewis dot diagram, so those diagrams we were drawing for elements in lesson 4.1, you can find out how many bonds an atom wants to form. Of course, atoms don't have like desires, but when we talk about how many bonds it wants to form, it's basically how many bonds would be needed to complete its octet. So if you have an unpaired electron, those are very reactive and tend to form bonds. Pairs of electrons, on the other hand, are relatively non-reactive and tend not to bond. So if I look at the Lewis structure of something like carbon, I see 1, 2, 3, 4 unpaired electrons. Carbon tends to form 4 bonds. Make a prediction about oxygen. Hopefully you're thinking that oxygen will form 2 bonds. These unpaired electrons, very reactive. Those pairs of electrons, those are pretty non-reactive. They're pretty stable and generally don't get involved in bonding. How about neon? Well, it's a noble gas. It has all pairs of electrons. That's why we tend to see no bonds, 0 bonds forming with neon. So we're going to try to take this concept and apply it to our Lewis structures. Let's start with the Lewis structure for CHCl3, trichloromethane, also known as chloroform. First order of business is to determine the total number of valence electrons we have to play with. This is a step that students tend to skip out on, and you can make really careless mistakes not by quickly tallying up how many valence electrons you have. Yeah, the math is not difficult, but it is important. I've got 1 carbon atom, and I know carbon has 4 valence electrons. I've got a hydrogen with 1 valence electron for a total of 1 electron from hydrogen. And then I've got 3 chlorine atoms, each with 7 valence electrons. So 7 times 3 gives me 21. I add those up. I've got 26 total electrons to account for in my Lewis structure. Valence electrons can move. We can put those 26 electrons kind of anywhere they need to be in order to complete octets and duets and make this as stable of a molecule as possible. but they can't change. You can't create or destroy electrons. So we need to make sure at the end, when we're finished with our Lewis structure, that we do in fact have, in this case, 26 total electrons. We're going to determine which atom is the central atom. Most of the molecules that we look at this point in the game are going to be small and have like one atom at the center and then other atoms sticking off from it. The central atom forms the most bonds. We've got hydrogen, carbon, and chlorine. Hopefully you're thinking carbon should be the central atom. Carbon's got 4 unpaired electrons, so it will try to form 4 bonds. We can then arrange the remaining atoms as symmetrically as possible around the central atom. So I'll take my hydrogen, and for no particular reason, I'm going to put it on the left of the carbon. You could put it on the top, the bottom, the right, it doesn't matter. And then I'm going to take my chlorines, and I'm going to do the same thing. Now you can see that the different elements have different colored valence electrons. That's just kind of so you can tell them apart. Carbon's got the purple ones, chlorine, the red, hydrogen is the green dot. If atoms are sharing 2 electrons, we're going to replace them with a dash to represent a bond. So just to go back for a second, these locations, instead of having them as just 2 dots paired up, we're going to use a dash, and that's how we communicate that a pair of electrons is being shared between 2 atoms. So there we've replaced the dots with a dash. Finally, check your work. Make sure all of the atoms have a full octet of electrons, and also make sure that you've got 26. Hydrogen, okay, it's got its 2, no problem. Carbon, 2, 4, 6, 8. Its octet is complete. Chlorine, 2, 4, 6. And those 2 that we counted for carbon also count for chlorine. So that chlorine has a complete octet, as do the other 2. Let's check and make sure that we've got all of our electrons accounted for. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Yeah, this looks like a pretty reasonable Lewis structure for the molecule CHCl3. Lewis structures take time. They take practice. Don't try to skip steps. Make sure you total up your electrons and then start, kind of working methodically from there. Let's try some practice problems. Okay, so I want to start with these 4 practice problems. And we're really just going to focus on the big blank, and that's just trying to draw a Lewis structure for each of those molecules. We'll deal with the shapes, bonds are, molecule is, in future lessons. So I'm going to walk through one of them with you, then I would encourage you pause the video, try them out, and then come back to check your work. So SiH4, silicon tetrahydride. I've got silicon with 4 valence electrons. I've got hydrogen with 1 valence electron each, so 1 times 4 gives me 4. I should have 8 total electrons in my Lewis structure. Silicon is able to form 4 bonds. It's most likely to be the central atom. Also, why would one hydrogen be the central with other things sticking off of it? If there's an element or an atom that's all by itself, high likelihood that one's the central atom. I know silicon has to form 4 bonds to complete its octet, so I'm going to just draw 4 dashes to represent those bonds. And conveniently enough, I have 4 hydrogens to fill. That's it. So try to take on H2S, NH3, and H2O on your own. Pause the video, try them out, and then we'll check them together. So I've added just a little bit of info about how many total electrons we have to play around with in each of these structures. Works out to be 8. H2S, I'm going to put sulfur at the center. H. Don't forget the unshared pairs of electrons. If I don't draw those, I only have 4 of the 8 electrons accounted for. If you drew yours as a straight line because that's more symmetrical, that is a perfectly valid Lewis structure. I would encourage you to draw it at this 90-degree angle because I know it's kind of coming down the pike for you, and that's going to make predicting the shape easier if you draw it at 90 degrees. Nitrogen, a pair of electrons that won't get involved in bonding, but it will form 3 bonds. 1 to each hydrogen. Lewis structure for NH3, ammonia. H2O. There we go. All of it, 8 of its electrons are accounted for. Real quick, if you look at those two structures, you should notice that they are strikingly similar. Why do you think that is? Our central atom is coming from the same group of the periodic table. They're both group 16 elements. And if you've got the same central atom, there's a really high likelihood that your structures are going to be very, very similar. So that's just kind of, I don't want to call it really a trick, but something that you can use to help check your work and maybe predict these shapes a little bit faster. All right, let's go ahead and get back to the notes. So I know we haven't drawn a ton of Lewis structures by any stretch, but those 5 that we drew, there are no exceptions. Our central atom wants to have a total of 8 electrons and complete its octet. If you went on and you tried to tackle the next row of practice problems, you might realize that you can't draw them just yet, and that's because the central atom for many of those are exceptions to the octet rule. So, yep, just like I said here, some atoms do not obey the octet. Certain elements, it's called expanding their octet, and they can hold more than 8 electrons. Other elements are unable to complete their octet. They're just not able to kind of wrangle all those electrons, and they have what look like incomplete octets. So you should know phosphorus is an exception. Phosphorus, if you were to draw its Lewis structure, you'd probably draw something like this, or its Lewis dot diagram, I should say. And you could see, oh, it wants to form 3 bonds. When it needs to, phosphorus can kind of like take that pair of electrons and split it up, making it look like it's got 5 unpaired electrons and ultimately can form 5 bonds. If you go over one space on the periodic table, you get to sulfur. Sulfur is able to do something similar. How many bonds do you think sulfur can have when it expands its octet? Yeah, it can have 6. It's kind of able to take those pairs of electrons, both of them, and split them to make it look like there are 6 places that sulfur needs to bond to. It's worth pointing out that what I've drawn for phosphorus is like an incorrect Lewis dot diagram right now. They should be drawn as paired up, but once an atom gets involved in bonding, those valence electrons are allowed to move wherever they need to go. Boron is another exception. Put some dots on boron. It only has 3 valence electrons. Boron can only form 3 bonds. You generally don't see it with a 4th. And the last one you're already familiar with, as we've done examples with hydrogen in it. Hydrogen will just form 1 bond. That just has the 1 energy level that maxes out at 2 electrons. There's no way you are getting more than 1 bond out of a hydrogen atom. So let's go back to the practice problems and try some of these out. Okay, so if we look at that second row, we've got some of our exceptions coming into play. And the question that students always ask is, well, how am I supposed to know if phosphorus and sulfur are going to kind of behave or if they're going to expand their octet? And my answer is always, you'll just know when you have to do it. And that is wildly unsatisfying because that's not a rule. It's just something that you kind of have to figure out as you're going through and doing the questions. So since we've already done one sulfur-containing compound, H2S, I want to look at another one, SF6. Sulfur has its 6 valence electrons. Fluorine, 6 of them times 7, 42 valence electrons. So I have 48 valence electrons to deal with. Sulfur is going to be my central atom. Oh, this is what I mean by it'll expand when it has to. There is no way to attach 6 fluorine atoms to sulfur without expanding its octet. So that is an example of sulfur accommodating those extra bonds that are needed by expanding its octet. And you are going to get very tired of drawing dots by the end of this unit, but I've got to account for all of my valence electrons, so adding the dots are essential. If we just kind of compare and contrast those two formulas, H2S with SF6, hopefully it's pretty obvious that here in H2S, there was no need for sulfur to expand its octet. It just had to form two bonds. But in sulfur hexafluoride, SF6, it has to expand. Otherwise, there is no way to accommodate all of those fluorine atoms. So pause the video, try out PCl5, BBr3, and PH3. I'll get the answers up. All right, so there are the answers. PCl5 and its 40 valence electrons. This is a case where phosphorus has to expand its octet so we can bond all 5 of those chlorine atoms. I'm going to skip to the last one. Here's PH3. Here's a case of phosphorus not having to expand its octet and kind of behaving the way you would expect it to. Also, if you look above it and off to the left, you can see NH3 and PH3 look strikingly similar. And yeah, they are in the same group of the periodic table. They're both group 15 nonmetals, so we're going to see really similar shapes. And finally, an exception in the other direction, boron only will form 3 bonds. It will not complete its octet. So boron tribromide, its 24 valence electrons should look like this. Boron at the center, all 3 bromine atoms bonded to it. All right, back to the notes. So far, we've only drawn molecules that have single bonds, but there are double and triple bonds that exist as well. So I want to talk a little bit about how to know when to draw them and how do we represent them in a Lewis structure. Sometimes when you're drawing a Lewis structure, it's going to feel like you've run out of electrons before all the octets are complete. And in your notes, talk about CO2. So let's see what we have going on here from a valence electron perspective. I've got 4 from carbon, and I've got 2 times 6 valence electrons for each oxygen. So that gives me 16 total electrons to work with. I know that carbon is going to be my central atom since it can form 4 bonds. 1, 2, 3, 4, maybe we'll do. I'll put an oxygen here. Okay, there's 1, 2, 3, 4. Okay, put another oxygen here, get those bonded up, and 2, 4, 6, 8, 10, 12, 14, 16. Those are all 16 electrons, but I haven't completed a single octet. I only have 7 around each oxygen. I've got 6 around carbon. This is what I mean by it seems like you've run out of electrons. I haven't completed any octets yet, but I don't have any additional electrons to plop down in my Lewis structure. That is almost a surefire sign that you need a multiple bond, be it a double or a triple. So in this case, what ends up happening are these 2 unpaired electrons are going to kind of push their way in between the carbon and the oxygen atom. So instead of just sharing a single pair of electrons, we'll see 2 pairs being shared and we'll get a double bond, and we simply represent that with 2 dashes. Same deal with this single electron on oxygen and this other one on carbon. Instead of being by themselves, they're going to kind of meet in the middle and form an additional bond. Now I still have my 16 electrons, 2, 4, 6, 8, 10, 12, 14, 16, but I've also completed octets, 2, 4, 6, 8 for each oxygen, 2, 4, 6, 8 for carbon. At this point in the game, if you have a Lewis structure drawn and there is an unpaired electron hanging out somewhere, you probably have done something incorrectly. While those do exist in nature, they're called free radicals, they are a little beyond where we are right now. So none of the structures you work with are going to have unpaired electrons. Just kind of a heads up. You know what we're doing next? Back to the practice problems. So this third row of practice problems are molecules that are going to require a double or triple bond. Let's start with like N2 and O2 first. I think those might be a little bit easier to deal with. So nitrogen, 5 valence electrons, 5 times 2, ooh, that's math I can handle, 10 valence electrons. Okay, they obviously have to be bonded to each other. I have not completed any octets, and I am out of electrons. That is a surefire sign that I need to form multiple bonds. Instead of those 2 electrons at the bottom of each nitrogen atom being by themselves, what do you think they do? Hopefully you're thinking, oh, they must get together and form a bond. You are correct. What about the nitrogen atom on the left and the right over here? Yeah, they're not going to be by themselves either. They are also going to form a bond. 10 electrons, 2, 4, 6, 8, 10 octets for both nitrogen atom. That is the correct Lewis structure for diatomic nitrogen. Oxygen, O2. We've got 12 electrons to play around with. Pause the video, try it out. Yeah, no way those are going to exist as unpaired electrons. Double bond between the oxygen atoms. Nicely done. Pause it again, try out CH2O and HCN. All right, so I've got CH2O drawn to the point where a lot of people get stuck. I've got carbon as my central atom. I bonded my hydrogens, no problem. Oxygen, carbon, no octets completed. I also know the carbon needs to have 4 bonds. Oxygen likes to have 2 bonds. So instead of drawing those unpaired electrons, I'm going to pair them up, share them between carbon and oxygen and form that double bond. Hydrogen cyanide, HCN, bonding carbon to hydrogen, no problem. Carbon to nitrogen, again, no more electrons, but I don't have complete octets. Instead of drawing 2 pairs of unpaired, unshared electrons on carbon and nitrogen, take them and turn them into a triple bond. Now I still have 10 electrons in my Lewis structure, but I've got complete octets everywhere. Those are the best representations for those molecules. Nice. Back to the notes. We're going to wrap up with kind of a more advanced topic when it comes to Lewis structures for covalently bonded molecules, and that is the issue of formal charge. So I want to get the notes down for you to get into your workbook, and then I want to look at an example. So it is possible that atoms within a neutral molecule can be positively or negatively charged. Not like an ion, but just kind of how the electrons are being shared. We talked about using the Lewis dot diagram for an element to kind of determine how many bonds it wants to form. If you have an atom that has more bonds than it wants, in other words, it likes to have a pair of electrons all to itself, but for the sake of making the molecule work, it ends up sharing those electrons. Since it's sharing that negative charge, it has more of a positive charge itself. Now those electrons no longer belong to it, but it's being shared with another atom. If you have an atom that has fewer bonds than it wants, so it's used to having an electron or 2 in a bond, and now for the sake of forming the molecule, it has to have those electrons on itself, unpaired and unshared, it has more of a negative charge. Again, we'll go through an example to hopefully make a little bit more sense of this. Whenever you are drawing a Lewis structure, you want to minimize the number of atoms that have charges. That's going to give us the most stable, most likely arrangement. So if you look at all of the molecules we've drawn so far, none of them have had charges, and that's a good thing. We want to really keep that at a minimum. So the rule that we're going to try to apply when we have to deal with a molecule with formal charge is if you can't give an atom the number of bonds that it wants, at least give them an octet. Let's apply this to a problem. All right, so let's take a look at O3, ozone. Ozone is a molecule that is going to end up with atoms that have a formal charge. O3 are 3 oxygen atoms with 6 valence electrons each. So I've got 18 valence electrons that have to be drawn in my structure. All right, let's try this out. Well, it's only oxygen, so I guess 1, 2, 3. At this point in time, don't try to form like a ring structure of any sort. You cannot make this a triangle. That is not going to exist. So there's 2, 4 electrons, 6, 8, 10, 12, 14, 16, 18, haven't completed octets. Well, I feel like I run out of electrons, so that's usually a sign that I need to share additional electrons. Okay, well, I guess I could take this pair of electrons and I could put that into the double bond. Now, at least I've got an octet of electrons around that. I'm going to draw these oxygens as different colors just to make them stand out. Blue, red, and we'll go green. So now at least like the green oxygen looks like it should be really happy with how everything worked out. It's got an octet of electrons, and it also has 2 bonds, just like it likes. This blue oxygen in the middle, well, it's got an octet of electrons, so that's good. It's not exactly what it wants from a bond perspective. It likes to have 2, it's got 3. And finally, the red oxygen, same deal. It's got an octet of electrons, usually wants to form 2 bonds. We've only given it 1. Here is where formal charge comes in. So the green oxygen has exactly what it wants, so it has no formal charge. The blue oxygen has more bonds than it wants. Usually it has its own set of electrons that belong solely to it, and now I've forced it to share. That's going to make the blue oxygen, the middle oxygen in this case, have a positive charge. It is oversharing. The red oxygen has a pair of electrons that it usually gets to put into a bond that now sits squarely on it. So that oxygen, the one all the way over on the left, the red one, is going to have a formal negative charge. The molecule itself is neutral. The positive one and the negative one cancel each other out from a charge perspective. And it leaves us with ozone. Formal charge, again, it's a little bit more of an advanced topic. It can be tricky, and we see it a lot of times when we've got multiple bonds present. The 3 ions directly below the example with ozone are good ones to practice with. But since this has already run pretty long, I'm going to let you play around with those on your own. Try to predict them. Check the answer key when you're done. Good job today, chemists. I know this was a tough one. Thanks for tuning in, and I hope you found this helpful.